Hello everyone, in this video I wanted to discuss the Mellin transform of the fractional part of 1 over x. And if you don't know, Mellin transform is the integral from 0 to infinity of the thing we're taking the transform of, multiplied by the variable to the s minus 1 power dx. I'm using x as a variable here. Now I want to show some connection between this and the zeta function. So if you don't know, the zeta function, zeta of s, is defined as this sum from n equals 1 to infinity of 1 over n to the s. As it turns out, this only converges when the real part of s is bigger than 1, assuming s is a complex variable. As it turns out, the integral above, though, which I'll highlight right now, actually converges for when the real part of s is in between 0 and 1. So it's of particular interest to us, and we'll talk about that right now. In fact, let me just write that this is essentially only valid for when the real part of s is in between 0 and 1. And to show that, well, we'll first do the following. We'll split this integral up as the integral from 1 to infinity plus the integral from 0 to 1. Now, if you don't know what fractional part is, it's just essentially the part after the decimal of a number. So for example, the fractional part of, maybe I'll write it down as an example here, but then I'll erase it shortly after. The fractional part of (3.2), for example, is just 0.2. The fractional part of pi is just 0.14159, or whatever comes after the 3. So the fractional part of a number is always going to be essentially what's left over after the decimal. So if you have the fractional part of any integer, it's just 0, where n is an integer. Okay. Also, in general, the fractional part of a number x, where x is any real number, is just the number minus its floor. And notice that makes sense because when you take the floor of a number, you get just the integer part only, in other words, the thing before the decimal. So subtracting the original number from its floor, or the floor from the original, you end up getting the decimal part left over. Okay, so with all that out of the way, we'll continue now. And the reason why I'm splitting this up is because this first integral is of particular interest. Notice when x is in between 0, or not 0, but when x is in between 1 and infinity, well, really we have x being bigger than 1. And notice when x is bigger than 1, the reciprocal, 1 over x, is smaller than 1. Smaller than 1. Sorry. And in particular, the fractional part then would be equal to itself, because it's just going to be 0 point something as a decimal. All right, so with that being said, in this first integral, we can actually replace the fractional part of 1 over x with just itself. And furthermore, 1 over x multiplied by x to the s minus 1 just becomes x to the s minus 2. The antiderivative of this is pretty simple. It's just x to the s minus 1 over s minus 1. The only part where this doesn't work is when s is equal to 1, but since we're assuming the real part of s is less than 1, that doesn't happen. Okay. Then evaluate between the limits, 1 and infinity. Plugging in infinity is a little problematic, but it essentially has to do with the fact that since the real part of s is assumed to be less than 1, then the real part of s minus 1 will be less than 0. So in other words, we have a negative power. So if you were to take the absolute value of x to the s minus 1, this, as it turns out, is just equal to x to the real part of s minus 1, which is the real part of s then minus 1, which of course will approach 0 as x goes to infinity because this exponent is negative as we see above. Okay. Pretty great. So we're in a pretty good position in the sense that the first integral simplifies as 0 minus 1 over s minus 1. So really it's negative 1 over s minus 1 in the end. Perfect. That's the first integral. The second integral I'm actually going to split up first as a sum. It's not obvious why I'm doing that yet, but I'll explain in a moment. So we're going to split it up as a sum of the integral from 1 over n plus 1 to 1 over n of itself. Now the reason why we're doing this is because I want to notice that the fractional part of 1 over x, you can take derivatives of that, but the derivative of 1 over x, notice, when you take derivative, is negative 1 over x squared. For the fractional part, it actually, believe it or not, is the same. And you can verify this by graphing, for example. That's one way to verify this. Another way of verifying this is just to kind of, well, imagine what happens like when there's discontinuities of 1 over x. And the only discontinuities of the fractional part of 1 over x occur when x is an integer. Well, when x specifically is the reciprocal of an integer. So if you had 1 over n, the reciprocal of the reciprocal is just an integer itself, n, which is 0 as we saw earlier. So this is why I'm splitting this up over reciprocals of consecutive integers, because those are where the discontinuities occur. Okay. So that's all I'm going to say there as far as that goes. And now we're going to use integration by parts. So to leverage integration by parts, I'm going to let u equal the fractional part of 1 over x. Du will then be negative 1 over x squared dx. Which again, if you're still kind of unsure why the derivative of this ends up being this, I recommend you graph the two and you can kind of see why. Essentially, if you graph the fractional part of 1 over x, it'll look very much like, well, something like this. I'm not quite doing it justice here, but essentially you have kind of these ramps, these kind of backward ramps, which if you actually shift up, so imagine shifting this one up, shifting this one up, and shifting that one up, you just get the graph of 1 over x. So you'll have to see that when you graph it yourself, and it takes a little bit of time to kind of figure out indeed why that's the case. It's kind of hard to say in words, but long story short, the fractional part of 1 over x, as far as change goes, trends the same as 1 over x, its non-fractional counterpart. So the derivative is the same because it just has to do with change, of course, rate of change. Okay, and now to complete the integration by parts, dv will be x to the s minus 1. So the v is x to the s over s. Forgot the dx here, but there we go. By the integration by parts formula, we have uv minus the integral of v du. It's all inside of the sum. Well, this integral now turns into the following. So it's uv minus the integral of v du. Now notice v du is a negative, so we'll make that a positive, double negative. And the over x to the second will actually decrease the power by 2. So we have x to the s minus 2 all over s. All over s, good. Dx. Kind of box that off to the side so it doesn't get in our way too much. And let me close the brackets here on that sum. Okay, so yeah, there's still quite a little bit to do here. This first guy is a little problematic. It's not too bad, but we have to recognize a few things. And that is that, remember that graph I was telling you about? If you take a look between consecutive reciprocals, 1 over n and 1 over n plus 1, it will look something like this. The graph looks like this. So of course, you end up getting 0 when you plug in the reciprocal of an integer directly, but when you're approaching it from the right, it actually approaches 1. So long story short, when we plug this into the fractional part, we'll get 1, but when we plug this into the fractional part, we get 0. So evaluating this, the first value will give us 0, and the second value will give you 1 times x to the s over s. And of course, x to the s in this case is 1 over n plus 1 to the s because of the evaluation. Okay. And now what? Oh, now this integral is actually very easy to deal with. Notice if you add 1 to the power, you get x to the s minus 1, and then divide by s minus 1, you get this. We have plus, and then we need to evaluate between these limits. Perfect. So now we're in a pretty good position and we're almost done, believe it or not. And it's going to be a little weird because we'll actually get the exact sum of, well, that the Riemann Zeta function is defined to be. Even though it's defined when the real part of S is bigger than 1, we'll kind of get a domain change because of a telescoping sum that we'll actually see right now, as it turns out. The first thing I think I want to do, though, is I want to factor a 1 over S out of the entire thing. We're going to do some evaluation here. So let me pull out the 1 over S first, I guess. So we get -1 times 1 over n plus 1 to the S. And then this evaluation becomes, that's all over S minus 1, so I'll write that first. And then we have 1 over n to the S minus 1 minus 1 over n plus 1 to the S minus 1, like that. Okay, so now what? Well, now I'm going to split this sum up. We're almost at the point where I like to be, but let's see. If I split the sum up, I'll pull the negative out for the first bit. So we get the sum from n equals 1 to infinity of 1 over n plus 1 to the s, which actually is very Riemann Zeta function looking. And then for the next sum, we'll have 1 over s, and I'll pull out the 1 over s minus 1. So we have 1 over s times s minus 1 times the sum from n equals 1 to infinity of this thing. And if you can't tell already, this is screaming out telescoping sum. And the reason why is because, and you can kind of see when you plug in values, when you plug in 1, this is 1 to the s minus 1, that's 1 over 2. That's the first term. When you plug in n equals 2, that's 1 over 2 to the s minus 1 minus 1 over 3. So you see the 1 over 2 canceled with the previous term. So if you're familiarized with telescoping sums, you'll know this thing just telescopes to just the value 1. Now, you may have to show some detail to show that it actually converges, but what you'll end up getting is actually 1 minus 1 over k plus 1 to the s minus 1, and then as k goes to infinity, that second fraction goes to 0, so you need to just get 1 there. So in total, we have the following. We have -1 over s minus 1 minus 1 over s times this guy, which, you know what, I'm actually going to re-index this, if you don't mind, at 2. So I'm increasing the starting value, so I'll decrease the variable by 1. So we get this, which is exactly zeta, but starting at 2, not at 1. Okay, and then we have this thing, which is that. Now, there's a few ways to continue. We can use partial fractions if you want, but in fact, I prefer just to combine these two. It's pretty easy to see what they combine to. Finding a common denominator by multiplying this top and bottom by s, we get 1 minus s all over s times s minus 1, combining those two, minus 1 over s times the sum from n equals 2 to infinity of 1 over n to the s. Now, s minus 1 and 1 over s are negatives, so when you cancel those out, you get -1 over s. -1 over s times -1 over s times that sum. You can clearly see what happens here. You can pull the -1 over s out, which I'll do right now. And what you end up getting left over is 1 plus the sum going from 2 to infinity. Now the sum going from 1 to infinity clearly has a first term of 1. So in fact, these two just combine into the sum from n equals 1 to infinity of 1 over n to the s. And what's that? That's just zeta of s. So in fact, we have shown that negative zeta of s over s is equal to the integral from 0 to infinity of the fractional part of 1 over x times x to the s minus 1 dx. And this is valid when the real part of s is in between 0 and 1. Now, I've actually seen this in a few different articles online, but I haven't actually seen a proof of this, so I think it's hopefully pretty useful to someone to see why this is true. Now, I know it's a little sketchy that we get the sum that's defined when the real part of s is bigger than 1 at the end of this, but this telescoping business is a little interesting because here I believe this sum actually converges when the real part of s is less than 1. And that makes this whole thing when you consider the entire sum convergent. In fact, it's all of this right here. There's some kind of change in variables that allows us to see that this is indeed convergent when the real part of s is in between 0 and 1. So it's something to look into, but definitely a treat to see. So I hope you all enjoyed this. Thank you for watching, and I'll see you in the next video.